So today we are back at it again, looking at these very interesting integration questions at the MIT Integration B 2023. We want to step back a little bit to the quarterfinals, fourth section, problem 3, and which is the integral of the flow function of square root of 1 plus 1 over x from 0 to 1. Now this week I thought I would call this a flow function integration week. So we'll look at a number of flow function integration problems and try to come up with just ideas on how to solve them. So with this problem, first of all, I would like to rehash and go back and look at what a flow function is. Flow function is a function that takes in an input, which is a real number, and it outputs a number that is an integer less than an integer less than the real number. For example, if you have 1.5, the flow function would take that and your output would be 1.0. The 1.4 input would elicit a 1 output. 1.8 will give you 1.0 still. If you had a negative 1.5, you would get a negative 2 because that would be the integer of whole number integer less than 1.5. And then negative 2.5 would be, the answer to that would be negative 3. So looking at that problem, it's very vital that we first of all envision the plot of that function. So this is how y is equals to square root of 1 plus 1 over x looks like. And this function asymptotically approaches 1 as x tends to infinity. So since we've been given the x domain of 0 to 1, we've got to look very closely at that 1 limit. Since the curve at 1 would be square root of 2, 1 over 1 plus 1 would be 2 square root of 2, which is about 1.414. That means that the flow value of that would be 1. So the value at 1, it doesn't really touch the curve. It becomes a little bit complicated for us here. And so we have to evaluate mechanically or directly the area of the strip stretching from x is equals to 1 to a point where we now have y equal to 2, which is at x equals to a third. So this strip here is really what would trip anyone if you're trying to solve this problem, and would have to like solve for that directly before we now consider the curve. So at 2, any values from 2.1, 2.3, all the way up to 3, all that would be 2. Now at 1.8, 1 over 1.8, 1 over 8 would be 9, it would be 8. 8 plus 1 would be 9. The square root of 9 would be 3. So at that point, we now approach 3, and again, it would be 3 the entire region until the curve is 4. So this is how step function really operates. And so we know how to compute the area under the curve stepwise from y is equals to 2 all the way. And so it's important that we also factor in this last strip. And the area for that, we call it A end, would be 1 minus 1 over 3, which is 2 over 3 times 1, which is 2 over 3. So when we compute the area all the way from x is equals to 1 over 3 downwards to 0, we'll have to add it up to this 2/3 to get the total area. So looking at that stepwise increase in values, that means that between a specific integer, for example 2 or 3, so between k and k plus 1, 1 over x within that interval would be square root of 1 plus 1 over x would be k, right? And so going down, if we square k and k plus 1, the square root sign disappears. And then we subtract 1 from both sides. We're now left with 1 over x is greater or equal than k squared minus 1 and less than k plus 1 squared minus 1. Then now we get the reciprocal of these values. So 1 over k squared minus 1 is greater than x or equal than x, or greater, which is greater than 1 over k plus 1 squared minus 1. So within this domain, x domain, the y equals to the floor function of square root of 1 plus 1 over x is k. Therefore, the integral from 0 to 1 of the floor function of the square root of 1 plus 1 over x is equals to the sum of these many strips, and within each strip, let's call it the kth strip, the value of this function is constant, and that is k. And so we integrate from the lower limit, which is 1 over k plus 1 squared minus 1, to the upper limit, which is 1 over k squared minus 1. And then obviously we have to add the area at the very end, the two-third strip that we calculated. So going forward to really evaluate this, this becomes now 1, obviously kx, and then you have this lower and upper limit. And when we substitute this in place of x, we get k over k squared minus 1 minus k over k plus 1 squared minus 1. And obviously we're beginning from 2, because the k is equals to 1 was complicated as we saw. So we're beginning from 2 onwards. And then next thing we'd want to do is to use the difference of squares. So k squared minus 1 is the same as k squared minus 1 squared. So it's the same as k minus 1 times k plus 1. And then this value here becomes k plus 1 minus 1 plus k plus 1 plus 1. So this ends up being, at least for the second term, being k over k times k plus 1. So the k's would cancel out, and then you're left with k over k minus 1 times k plus 1 minus 1 over k plus 2, summation from 2 to infinity. We can now use partial fractions here, and this results to a half of summation from 2 to infinity of 1 over k minus 1 plus 1 plus k plus 1, and then minus that second term that we had there. So we can distribute this, since this is half, we have 2 halves of the second term. We can distribute it accordingly so that we have now half of the summation from k is equals to 2 to infinity of k minus 1 minus 1 over k plus 2 plus, and we've taken this the other side, so we have plus a half of k 1 over k plus 1 minus 1 over k plus 2. So we can consider this as two sums or two summations, the blue and the green summations. And so if we focus on the blue summation and we try to look at it inductively or by induction. When k is equals to 1, we see when k is equals to 2, sorry, we see that that is the same as 1 over 2 minus 1, which is 1 over 1, minus 1 over 2 plus 2, which is a quarter. And then when k is equals to 3, this 1 over 2 plus 1 over minus 1 over 5. And then when k is equals to 4 is the same as 1 over 3 minus 1 over 6. And k is equals to 5, same as 1 over 4 minus 1 over 7. When k is equals to 6, it's 1 over 5 minus 1 over 8. When k is equals to 7, it's 1 over 6 minus 1 over 8. Now, if you look at these values, we see that their quarter here cancels with the quarter here, right? And then their fifth there cancels with the fifth later down the road. The sixth there cancels with the sixth down the road. And the cancellation will continue all the way up to infinity, but we are left with these first three terms that are not going to be cancelled. So that sum is the same as 1 plus a half plus a third. Then the second sum here is when k is equals to 2 is 1 over 3 minus a quarter. When k is equals to 3 is 1 a quarter minus a fifth. And then when k is equals to 4 is a fifth minus 6. And then we see that a quarter and so on. And you see that a quarter here cancels with a quarter there. A fifth there cancels with a fifth there. Sixth there cancels with a sixth there, and so on. So we're left with only a third at the beginning. These are what we call telescoping series. So you have two values that the second value now cancels up with the successive terms, and you're only left with the initial term. So these are telescoping, a very common concept in series summation. So the blue, as we saw, it has 1 plus a half plus a third, and this we see it as a third. So then what we have now is that that summation is the same as half times what we computed, which is 1 plus a half plus a third, plus a half times the green summation that we just computed, which was a third. So this now results into a half times 1 plus a half plus 1 over 3 plus a half times 1 over 3, which is the same as 13 over 12. So the integral that we saw previously of the flow function is the same as the summation term plus the area at the end, which is 13 over 12 plus the 2 thirds that we computed initially, and that results into 21 over 12, which is 7 over 4, our final answer. So really, thank you so much for joining us this evening again. It's been a wonderful time providing this solution to you guys. For those of you who have not subscribed to our channel, I really encourage you to subscribe to our channel, especially this week where we're going to focus on flow function, which sometimes is very hard for some people, but we are going to try and use simpler ways to visualize these problems. So I encourage you to click on that subscribe button so that you get that notification every time we are solving a new problem. Thank you again. Until next time.